me? Okay, good. Okay, I think we can start now. Okay, afternoon everyone. So today we will study the last content of the courses. This is about the matching problem and the maximum flow algorithm. So next week is just about the review lecture. Okay. So yeah, I think this week content is more about teaching you about this kind of very important problem, the matching problem, using the maximum flow algorithm. So this one will not be tested in the in the lab test too. Okay. So, but anyway, I think you should know about that because this is a quite important problem. Okay. So we go to the matching problem. Okay. So this one, for example, we have a graph that you can partition the vertex v. Okay, the list of vertex v into the two set J and W. Okay. Then so for example, we can separate like that in the graph, and then for every edge in the J will connect to the one in the W. Okay. One in J connect to one in W. So this graph is called the bipartite graph. Okay. So it means that we can separate into the left hand side and so there are J, so there are the W. Okay. So J connect to W. Okay. And for the matching problem, you can see like for example, Tom, like it's just like you have the people on the left hand side, and this is the action on the right hand side. Okay, the people will have a few actions. Okay, and for the matching problem, is a for one people on the left hand side is should be connected to only and one and only one action on the right hand side. So that's it. We call it the matching problem. For example, this one we can find a matching, right? So that every each people on the left hand side can connect to the each action on the right hand side. Okay. So like this one, we can have three pairs, right? So matching is just a subset of the edge that are mutually non-adjacent. Okay, and no two edges have an endpoint in the common. Okay, so this is they call it the matching problem. It means that one on the left hand side can connect to at most one on the right hand side, and vice versa. Okay. Yeah. So this is they call it a matching problem. So it's just like you have many candidates and a few jobs, right? You need to match it so that the candidate can only pick up one job, for example. Okay. So the problem is whether we can matching with the maximum number of edges. For example, for the original like this, right? We can have a few match, right? For example, you can match okay, this one you have the maximums, right? Because we have the maximum 3 people and 3 jobs. So the maximum one is 3 edges, right? So that's the meaning, the problem. So given the relation between the left hand side and the right hand side, so we need to find the matching with the maximum number of edges. Okay. So do you have any question about this? So the problem is quite clear, right? Actually, you can also have match this one with this one with this one, but we only have 2, right? So the maximum should be 3, something like this. Okay. Yep. So this is the matching problem. So the matching problem, the lab question will not be tested in this chapter. Okay. For the quiz also, I won't test you the quiz question on this chapter. So this one is just, I teach it this one for your knowledge. Okay. So I won't test this in the final quiz and also for the lab test. Yes, we only have 8 lab, and lab 8 is the last lab. Okay. So another one, we also need to study about the network flow. So what is the network flow? They say we introduce so this one you see this just like the weighted graph, right? Okay. And the network flow is just we have the source and the sink. So the flow will flow from sources to the sink. Okay. Then then the flow we can have it's just a directed graph from S to T. Okay. So every edge will have a weight. They call it a capacity. Okay. For example, S to B, this means that we have a path from S to B. From S to B, then the capacity is 10. Okay, so the maximum capacity that the flow can be flow from S to B. Okay. So actually the maximum matching and the maximum flow can be equal problem. Okay. So for example, this is the maximum matching, right? You have the connection from J to W. Then you can convert it into the flow. Okay. You just put, the source and the sink. Okay. Then the source connect to on the vertex from in J, and the sink will connect on the vertex from W. Okay. Then if there is a connection, then the capacity is 1. Then the maximum matching is just similar to the maximum flow. This means that at the end, right, you just count how many, the flow can be go to T. Then this is the maximum matching. Okay. So for the, for example, you can see this one is but in the general, this is the network flow. But for the maximum matching and the maximum flow problem, if we convert the maximum matching into the maximum flow version, then every edge have the capacity 1. Okay. So if they're the edge, then their capacity 1. Then we need to find the flow. Okay. So that it can, have the, on the flow can be go to here. For example, if we choose this one and this one and this one and this one, right? Then we cannot satisfy because the flow here is 2, right? Because one here, you can see at this knot, right? So 2, the capacity will be 2, right? 1 here and 1 here. So it can only go through 1 here. Okay. So it means that one of this cannot be happen, right? Because the total capacity is 2 here, but this capacity only 1. Yeah. So the maximum flow is the one that we need to find the condition so that, okay, every edge have the capacity. It cannot reach more than capacity. Okay. So we're talking about the network flow in general. Okay. So the network flow in general, we mentioned like we have the source and the sink. Okay. Yeah, I just mentioned. So the problem matching will not be tested in the lab test and also in the quiz. Okay. So it just I teach you just for your knowledge. Okay. It won't be tested in the lab and the quiz. Okay. Okay. Anyway, we back to this one. So we have the network flow. So the source and the sink. Okay. Then we know that there's the directed graph, right? And the flow will be the integer function f. Okay. So that we chosen so that the flow will less than the capacity. So each edge will have the capacity. So the flow, of course, must be less than or equal the capacity, right? And we want to maximize the flow allocation so that the total volume will be go through the T will be maximum. Okay. For example, this one. Okay. You can see. Okay. Yeah, this is the. I mean, this is one of the network flow. So we need to design something so that okay the flow here. For example, if we put this one right, then this one will be overflow, right? It will keep 10 and 1 here. It will overflow because it 11 is more than the capacity. So of course, this one you cannot go to the C with a maximum 10 and 1. Okay. So you look at this. We I mean in this one we will denote the capacity in the blue color. Okay. So how to find the flow that we can maximize the flow allocation? Okay. So this one is just some example. Okay. So for example, this one is the flow network. Okay. So actually you can see the first one. Okay. You can go to the first one. Okay. The flow can be flow from S to A to C, C to S, C to T, right? Then this satisfies the condition, right? If there's a flow like that, because the capacity on the flow color is 10, and we just flow 10, then it's okay, right? Because it's still, I mean, on the capacity, okay? So the dark light is the one flow, okay? Another flow is this one, right? Okay. So the flow is on the red color. You look at this. So if we put the flow 1 here in this path, and then it's okay, right? Because the capacity on this edge from S to B is 10, but we only flow 1. Okay, 1 is the flow and 10 is capacity. Okay, that is still okay, right? Because it's less than the capacity. And this edge also okay. B from D also okay, because the capacity is 1 and the flow is 1. And similarly from D to T is also okay, because the flow is 1 and the capacity is 1. It means that we can flow the fluid from S to T, right? With the volume is 1, then it's okay. Then we have two flow right now, right? Sorry. We have two flow right now. It's from SACT with the volume is 10, and another one is SBDT. The volume is 1. Okay, so it means that at that time the sink, right, the total amount a sink can get is 10 and 1. 1. 10 and 1 or 11, right? So the flow of the side is 11. But is it a maximum yet? Okay. Do you see whether it's maximum yet? Whether is it the maximum size that the sink can get? I mean, if you look at carefully, right? So actually, you have one more thing, but this one is not obvious. For example, you flow 10 from S to A, okay? But from A to C, you only flow 9, okay? And you flow another one from A to D. So it means that you have a new two path. This one, okay, this path, okay, and this path. Okay, then you increase the volume here is 2 so that it can come to B, right? It 1 go to B to C. 1 go to B to D. Similarly, you increase, you 10 here, right? But you only flow 9 to here, okay? And 1 you flow to here, A to D, okay? Then from D, right? Because D can get from A, can get from B with volume on the side is 1 plus 1. So the side from D to T will be 2. And similarly, SC, right? You get 9 from A. 9 from A. And then you get 1 from B. 1 from B. B flow 1 to C. So the C still have the, the total size is 10. So it means that from C you still can flow 10 to T. And from D you can flow 2 to D. So the total flow now is 12, right? So it means that the maximum, so they bigger than the previous one, okay? So this one is, and this one can be considered like the maximum flow we can get, okay? But of course, you can see this one is not obvious, right? How can you find on the flow here? It looks quite complicated, right? Because you need to, plan how many things, for example, from S to A, right? Is 10, but you need to plan so that 9 only go here, 1 go this way, okay? In the step 2, right? You can see S to A is 10, you flow everything to C, but then the maximum is only 11 you can get. But if you from S to A 10, right? But A to C you only flow 9, and 1 you go to D. Okay. Similarly, you can increase the S to B to 2, then 1 go to C, 1 go to D. S to B is 2, right? And from B, 1 go to C, 1 go to D. Then the total size that the thing can get is 12. Okay. So that's the the problem. How can we find the number 12 here? And how can we find the the path like this? So that we can maximum the size that the thing can get. Okay. To solve this problem, right? Actually, there is one famous one they call it Fulkerson methods. Okay. The four Fulkerson methods. So they are just an iterative improvement strategy proposed by the four and two scientists, mathematics, I think, mathematician, Ford and Fulkerson in the 1956. So it's either iteratively find an additional flow match in the network. Okay, so I will teach you step by step. So actually, how to find the additional flow? They use a residual network to find the available flow. Okay, then the residual network will calculate using this formula. So the residual from the not J to W would be the capacity from J to W minus with the flow from J to W. Very similar. Very simple. It's just like the available one, right? For example, if you had a capacity 10, but now your flow is only 2, it means that you still have 8 more to flow, right? So this method is just iterative to find the additional flow so that you can flow into the network that not violate the condition. That's the flow cannot more than the capacity. Okay. So how to do that? So they just do the augmenting the path. Okay. So at first, right, for example, you have the network. Okay. So they are network. Okay. With the flow, right, from the left to the right. Okay. Then at first, okay, the flow is just, the flow they given, like, for example, 1, 2, 3, 4. So they are the flow, okay? So at first, you build the residual graph, right? You just calculate the value, like the capacity minus the flow, okay? And at the beginning, the flow will be 0. There's no flow yet, okay? So when you choose the flow, then you will update the residual graph. And then when you find the residual graph, you find the path from S to T where the positive residual value, okay? And after you can find the available one, you will increase the flow so that it will augment with a minimum residue along the path, and then we keep augmenting. Okay, so they are the theory. I mean, they are quite complicated. Yeah, the capacity can be more than one. In general case, in the flow network, okay, capacity it's just like the flow, right, from one point to another point. So how many? I mean, why the capacity can be 10 or 100? Okay. So there one example of the residual graph. So this is the original graph, right? They give us. So you look at the beginning, right? So it's just a 10-10, okay? The flow is the capacity they give us. For example, the capacity, this one, they just give us this one, right? So the original graph. We need to build the residual graph to find the available one, okay? So the original one. So the flow one, the blue one is the capacity, okay? Now we need to find the, I mean, on the path that we can maximize the total size that we can get from T, okay? So for example, you had the original path, right? Then you can see that at the beginning, there's no flow. Then you can see that, okay, there's one path from S to T. This is one path. Then what you do? You just, this code actually, I mean, we have the algorithm, then you just follow this. Then you can implement this. I mean, I just teach you the theory and the intuition behind. Then later I will go provide the I mean, algorithm. Then you just, I mean, do the coding following the algorithm that it can work. Or you can Google, I think there's so many available code, okay? But anyway, we start with, I mean, the empty one. I mean, there's no flow. Then we find one path from S to T. Then the path is from S to A to C, C to T, right? Then we choose the minimum amount of path. But among the path, the minimum capacity is 10. So it means that at the beginning, okay, we just flow the maximum available. So it will be 10, right? Because on the capacity here is 10. Then it means that if you flow from S to T, you can flow 10, right? Because on the maximum, I mean, on the capacity is 10. So it means that you can flow 10, right? In this path from S to T, right? So therefore, when you calculate, right, you calculate the capacity minus the flow, okay? So it means that 10, 10, capacity 10, you use 10. So the capacity will be, I mean, the available will be 0, right? So you cannot flow, okay? You cannot flow more in this path, correct? Because they are maximum capacity. Then if there's 0, then you just reverse the, I mean, the flow, okay? So if there's 0, right? So you can see in the residual graph, original residual graph will be similar to the residual, I mean the actual graph, the original graph. But then because when we flow first, we had the first flow from S to T, okay? From S to T with the flow, the size is 10. Then on the remaining available one is 0. Then we reverse the flow, okay? So it means that from S to T, you reverse the flow from T to S, like this. You can see on the, I mean the direction reverses, okay? Previously from C to T, now reverse to T to C, okay? And the value will be similar value of the flow is 10, okay? It means that, okay, just like that, you can see the connection, right? If you can flow from A to B, it means that you can also flow from B to A, right? Because it's connection, right? But anyway, we know that, okay, this is the flow, and the rest we just, I mean, keep the same, okay? Then you look at the residual graph. again after we do the reversion, right? You look at the result graph. You see whether any path can be from S to T, any additional path. Then you look at the green color. This is the additional path, right? From S to T, okay? And what the flow, the maximum flow we can flow in this path? What the maximum flow if we flow from this path? You see, 1, right? Because here, we had a bottleneck here. Even though this one can flow 10, but go to here is only 1. It means that maximum flow, if we flow from S to T, from this part, only 1, right? Correct? So it means that we update the original graph, the residual graph, okay? So, okay, we have another path from S to T, okay, there 1, okay? Okay, then we update the residual one. You remember, residual is just the capacity minus the flow. And if the residual graph is 0, then we reverse the edge. Okay, so you can see we have the residual graph, right? We update, right? So now we have this one, right? 1 from B to S, 1 from S to B, right? So we also have the reverse B to S, right? So we reverse the one that we already have the path, right? From S to T, then we reverse T to S. You can see this one, T to S, we reverse with a capacity 1. But we also have, because original, we have that from S to B 10, right? S to B is 10, but we use 1. So that's why we update the residual from S to B is 9, minus 1. So available, their current available is 9, right? Similarly for D to T, so we also available 9, right? So that's why we update the residual graph like this, okay? Then we have this one, okay? Then we look at the residual graph. Any available path that can go from S to T from the residual one. You can see from S to T, you can see 1. From S, they go to, okay, I clear this one, so easy to understand. So now is a update residual one, right? Then we go to the next step. We need to find available, next available, any available from S to T. We have 1, right? We go this way. S, we go to B. We still have, right? E nice, right? Then B, you go to this way, the path. C. Then C, you go to this way. You look at this, right? And from A, you go to this way. And then A to D. And then from D, you go to this way to T. Right? You can see, right? We have 1 path to go from S to T. Then this one will be the additional one. Then we can flow in this path. And what the flow, the maximum flow we can flow, then we look on the capacity here. From S to B is 9, right? What? We can flow, right? Because we can say S to B, B to C, C to A to D, D to T. Okay. Then what is the maximum flow? We can flow from S to B is 9, B to C only 1, C to A can be 10, A to D is 1, and D to T is 9. This means that maximum flow we can flow is 1, right? Correct? This means that we can flow 1. Then we update the things. Flow 1. So it means that it will reduce to 8, right? Okay, this is the things, and we update it in the original graph. Okay, because we flow one in this path, right? So we update the flow. Okay, because we flow one, you can see original is 10. This one first. Original is 1, right? But we flow one more, so it will be 2, become 2. Okay. Then from B to C, from B to C, original we don't flow, but now we update that we flow 1. Okay. How about from C to A? From C to T. Okay, you update the, you can see, right? This is the path we go, okay? Right? So we update the residual path, okay, first, okay? So now the residual one is from S to B, okay? Sorry, from S to B. Original is 9, now it becomes 8, because we flow 1. From B to C, I delete all the things. B to C is 1, right? Now we use on the capacity. It means that we have the reverse one. It becomes C to B. You see? C to B. Because it used on the capacity. Then reverse one, C to B. Okay. Then the C to A. Original is 10, right? Now we use 1, so it's become 9. Then because we use 1 from C to A, so we draw one thing from A to C. 1. Okay. Then next from A to D, right? A to D, original is 1. We use 1, so that's why we reverse this. Okay. D to A. Okay. Then from D to T, we have 9 in this one and 1 from the reverse one. Now we flow one more. It means that we reduce 9 into 8, and the reverse one we increase to 2. Okay. It means that whenever we flow one A from A to B, right, then we create another reverse one. Okay. Then from this one, we update the original graph. Okay. Original graph, you see the difference between the previous one and the current one. Okay, then you can see. So this is the final one for the residual graph. Okay. Now we look at the original graph. Okay. G. Okay, we look at this one. Previously, we have only 2 flow, right? Now we have additional flow. Okay. So what the additional flow you can see here? There, this is from here to here, right? Right. So from here to here. Okay. So now previously it's 1, right? And 0 here, no flow. Then we update it into a flow. Okay, 2 and 1. And previously, this is the capacity. The flow is 10. But now we have the residual 1 here, right? It means that we need to reduce 1 from A to C. Okay, A to C. So previously we have 10, right? We reduce 1. So it's 9. Okay. Similarly for A to D. A to D, previously we have no things, right? No flow. Now we have a new flow is 1. And D to T. D to T, previously we had a flow is 1. Now we have the new one is 2. Okay. Right. So then finally we have the, we update the, the rough G like that. Then you can see what the actual final flow you can get. So you have the S to A, right? S to A with the flow is 10, right? Then from A, they will split into C and D. So A will go to C with the flow is 9. A go to D with the flow is 1. So it's okay, right? Because S to A is 10, then it's split into 9 and 10, 1. Okay. Similarly, S to B will be 2, right? But from B, they will split into C and D. So B to C, the flow is 1. And B to D, the flow is 1. So why the C can get? C can get 9 and 1, right? 9 from A and 1 from B. So the total one, they can flow to T will be 10. Okay. So C total can flow to T is 10. And D similarly, D gets from A to B. So D flow to T will be 2. So it means that at the end, T will get 12, right? At the end, T will get 12. Okay. So that is the maximum flow. Okay. So for the flow network, there's a few things you need to notice, right? Even though the capacity can be high, but because of the bottleneck in the network or something, the flow you may not utilize on the capacity. For example, this one at the end, right? You only from S, right, to B, right? Even though the capacity is 10, but you only flow 2 because the network cannot stand for more than 2. Because you can see at B, we bottleneck at B. B have two connection, right, to C and D, but the maximum capacity only 1 and 1. So maximum flow that B can get is only 2, right? So that they can flow to C and D. Okay. So again, think it's just like the water pipe. They have the capacity, but you cannot put so much water into, right? Otherwise it's broken. Yeah, something like that. So you can think that the flow network is just like the water network, right? You have the source is like the one that the water supplier, and T is your house, in many way to your house, but because of the pipe capacity, that even though network can be very, very high, high volume, but go to your house, it's just like a smaller volume because of the bottleneck in the network. Okay, and the problem is how much is the maximum water that you can get, okay, based on this network. Okay, and for focusing methods is one approach that you can use that help you to find the maximum value. Okay. Then this is the one illustration of the methods of the algorithm. On Friday, I will give you the actual algorithm. Okay. So that you can follow the coding. You can follow the algorithm. Okay. But the idea of the algorithm is just you maintain the residual wrap. Okay. And then from a residual wrap, you can see whether you can have any available path that you can flow into the network or not. Then if they're available, then you add this path into the network and update the residual graph until you cannot find any additional path from the source to the sink. Then we stop. So it's just like the algorithm is just like the iterative methods. every time they find whether any additional path or not. If they additional path, then you adjust the network according to this path. Okay. Yeah, so I think today is today is we stop here today. So next week we will see how we can apply the network flows for the PyPath type matching problem. Okay. Yeah, this is for Friday. Okay, so we stop here. Okay, so let me see, any question for you? So whether I can give a practice question to do before the lab test. Frankly speaking, right, for the lab test, right, I won't challenge you so much. You can find a practice question in the LeetCode or the HackerRank or some programming side. But actually, the question there is more difficult than the one in the courses. So frankly speaking, right, for the course, I can only advise that you look at the lecture, the slide in the lecture, you understand about the concept behind, for example, what the concept of the depth first search, breadth first search, backtracking, and backtracking and dynamic programming, right? And then you practice the lab question and the assignment. Okay. And then I think I'm sure that you can do the lab test for sure. Okay. So no worry much about that. Yes, the lab test will be similar difficulty level with the lab question, except there one question that a bit challenging. Okay. But it's just about thinking a little bit about what I teach in the lecture. So that's why I said that you only need to look at the lecture carefully and understand the lectures, then you can do the lab test easily. Okay, especially about the intuition of the algorithm I teach. For example, breadth first search. Why we need the breadth first search? And breadth first search can help you for what? For example, breadth first search can help you to reach on the reachable node in the network, something like that. Yeah, you can see the assignment, right? Even the assignment, I also test you about the understanding of the concept and the intuition of the algorithm. I won't challenging you about the programming skills or something. I won't challenging that. I just make sure that you understand about the concept of the algorithm. Okay. So yeah, that's it. Basically, right? Yeah, you just need to use the certain function to get the certain answer. Correct. And for all the supporting function, for example, when we do the backtracking, for example, for the n-queens, right, or something, then we'll provide you during the lab test, and we'll also provide you the supporting function, for example, the e-safe or something. So you don't need to care about this. You can just call okay e-safe, and it's okay. Then they check the whether it's safe. So you only focus on the algorithm things. So on the supporting function, I will provide to you. So no worry about that. So the only thing you need is your understanding about the problem and how to solve this. That's it. And if you actually, frankly speaking, if you understand about this, then you can solve the problem in just a few lines. But if you don't understand, then you cannot solve it. But we will have, okay. So talk about the final quiz and the final quiz and the lab test. I think I mentioned before, right? So the final quiz and the lab test will be combined into one. So it's just like the lab test one, right? So this one we will combine the final quiz and the lab test into one. So you will have 2 hours, okay, for the final quiz and the lab test. And the format will be similar like assignment. You will have 10 questions in the MCQ part and 3 questions in the programming part. So 10 questions in the MCQ part will be the final quiz, and 3 questions in the programming part will be the lab test 2. Okay, so I just combine two things together. So you will have total 2 hours for the final quiz and the lab test. It's up to you to arrange the time. Okay. So 10 questions in the MCQ. This is a final quiz, and 3 questions in the lab test. So this is the 3 questions in the roaming. It will be the lab test 2. Okay. The day is 21 April. And we will have 2 sessions, morning and afternoon. It's just exactly like the lab test one. So the morning will be the morning session will be from 10:30 to 12:30, and then the afternoon session will be 2:30 to 4:30. And if you are in the morning session in the lab test one, then you will be in the morning session in the lab test 2 and the final quiz. So I will reduce the same arrangement. Okay. I will reduce the same arrangement. So if you are in the morning session of the lab test 1, then you will be the morning session in the lab test 2. And similarly, if you are in the afternoon, then you will be in the afternoon for lab test 2. Okay. Then for the lab test, yes, we have 2 normal questions. So the normal question will be simple like the assignment, or even though easier. And then 1 challenging question. Okay. But challenging question is about your understanding. Okay. So it's not much about you need to program very long. It's not about like that. It's just about you need to understand. Okay. So that's the the arrangement. Okay. A little bit more difficult than assignment. But it's about testing you about the understanding. Okay. But we only have 1 challenging question. We have 2 easy questions. Okay. The easier question will be same level like the assignment, or even though a bit easier, because for the assignment you have longer time to do, right? And all the question is about testing you about the understanding about the things. Okay. For example, for example, like in the assignment, right? We study about the breakfast search and default search. Then in the in the lecture we study about breakfast search and default search. But you know that, okay, breakfast and default can be used to find on the connected path, right? And the connected vertex, right? Then in the assignment, I just ask you to give the program based on the default and breakfast to check whether a graph is connected or not. I mean, it's just like that, right? Okay. Of course, I cannot give 3 easy questions in the lab test, because otherwise all of you got the maximum score. So that's why I keep 1 challenging question. Okay. And for the quiz, we have 10 questions in the quiz. 5 questions will be in the part 1. So that's why Dr. Locke will give me the question. So this one I cannot control. Okay. Then 5 questions will be in the part 2. Okay. Then the question of the quiz in the part 2, right, will be similar difficulty level like the question in the assignment. Okay. Okay, for the quiz in my part, for the part 2, the difficulty level for the quiz will be similar like the difficulty you got in the assignments. Okay. And this one, I'm not so sure whether you think it's difficult or not, but it will be the same difficulty level like in the assignment. Okay. Then next week maybe I can go through next week we have the review lectures, right? I can also go through the question in the assignment. Okay. So that if you have any question about the assignment, for example, 4 and 5, then I can go through this next week. Okay. Or also about the question, the programming question in the assignment 4 and 5, I can go through there. Okay. For the assignment 6, I will release by the end of this week. Okay. So assignments 7 and 8. Okay, 7 and 8. I will release by the end of this week. Then it will combine. Yeah, 7 and 8. 7 and 8 will be combined. Okay. For the past assignment question, right? Sorry, I cannot release because the policy of the university. We cannot release the question in the assignment or things on the NTU Learn or something. So that's why in the review lecture, I can explain blah blah verbally, but I cannot post it in somewhere, okay, in anywhere. Okay. So for the this chapter about the matching, I confirm. I mean, confirm that there no testing, no programming test, and no quiz for this this chapter. I mean the matching problem. Okay, so no worry. Yeah, so that's it for on the things. Yeah, I will make sure that at least you can do something in the final quiz and the lab test. Okay. So for the reversing the flow, it just for the residual network, right? I mean, if in the original graph we can have one flow from A to B, then in the residual network we create another reverse one from B to A. Okay. It means that from A to B we already flow. Then we can only flow back from B to A in the residual network. Okay. I think for the student feedback, I already closed. Yeah, it's closed. I think it's closed in week 11 already. Yeah, 10 or 11. Yeah. Anyway, I think I got the very supporting reviews, feedback, and also reviews from you, because this is the first time I teach the classes. Yeah, but I got a lot of valuable feedback, positive and negative. Then it's very helpful for me so that I can improve it in the next years. Or yeah, I just joined our school last year. Yeah, so this is the first time I teach the classes, the lecture. So hopefully that you can enjoy the course and won't get the nightmare of this. Okay. It's more than 4. So yeah, luckily. I mean, some comment, very constructive comment like my action or something. Yeah, I will try to improve it. Yeah. Yeah, and because of first time, so there is something that not quite fluently. Yeah. This course had a bell curve. I think so, but the bell curve form. I mean, we can free to adjust. So no worry. Okay. So if you have the good score, for sure you won't fail, or you won't have the low score, low rate. Yeah. I mean the size of the bell curve we can determine. So no worry about that. Okay. Of course, if you get like 70 over 100, and you won't get B for sure. For the lab test, like I mentioned, right, you can practice in the LeetCode or HackerRank, but they are normally very hard, right? Harder than the question in the harder than the question in ours. So that's why I think you only need to practice by looking at the lecture and practice in the lab question and the assignment question. I think that's enough. The rate scheme, actually, this one I'm not so sure, because after you finish the exam and I need to discuss with Dr. Law about how we adjust this one. So this one I cannot tell now. Okay. Sorry, 70 over 100 should be B, right? Yeah. 7 over 100 should be B, right? Yeah. I mean, according to our NTU system. Yeah. I'm not so sure. I mean, it depends on we'll adjust it later. So no worry. I mean, you only need to do the test well. Then I think your score should be okay. I mean, if you do well, then your score should be good enough, right? Why you care about the rate? Well, anyway, I will try to make the curve a little bit better for you. Okay. But the curve right now we haven't decided yet. I mean, not really. I mean, for example, for the assignment, many students, I don't know why they didn't do the assignment also. Quite many students. For the assignment 5, there's so many students didn't do the assignment 5. Didn't try to attempt it also. And of course, not all of you got the maximum value, maximum score for assignment 5. So I think if you do well in the assignment and the lab test, then the score won't be so low, I believe. For the assignment, I need to check with the school whether I can release the score or not, or when, if I release, when I can release, because there's some regulation I need to follow with the school. For example, some past paper, some question I cannot release online, something like that. So this one I need to check with the school. Okay. Okay, yeah, somehow my computer dropped. Okay, so any more questions? Otherwise, I think if you don't have a question, you can leave. Otherwise, you can ask me. 7A not so difficult. Yeah, not so difficult. So no worry. Assignment I won't make it so difficult. Okay. So see you. Bye.